evening, and welcome to this lecture in our leadership lecture series featuring our alumni. In a break with tradition, we are going to start this program with an invocation song because the speaker's wife today, Mrs. Vidya, is an accomplished singer as well as teacher. So I want to take advantage of her presence today. I'll invite her to give us a brief invocation song.
श्रीवातापि गणपतिये निन्तिरुवडिये शरणम् ॐ श्री वातापि गणपतिये निन्तिरुवडिये शरणम् ॐ श्री वातापि गणपतिये देवादिदेवन् त्यागेशन् देवादिदेवन् त्यागेशन् திருவிளையாடல் செய்திருவார் ஊர்வலசி வாதாபி கணபதியேனின் திருவடியே சரணம் ஓம் ஸ்ரீ வாதாபி கணபதியே நம்பின பேர்க்கீக்கபரம் இரண்டிலும் நல்வாழ்வும் பேர் இன்பமும் நல்கும் தும்பி முக பெருமானே அடி தோழும் தொண்டர்கள் வேண்டும் முன் வரம் தருவோனே சம்புவுடன் கமலாம்பிகை மகிழும் தனயனே தயாகரனே ஜகம் புகழும் கும்பமுனி கருள் குமரன் முன் தோன்றிய கோமானே ராமதாசன் உள்ளம் வளர்ச்சி வாதாபி கணபதியேனின் திருவடியே சரணம் ஓம் ஸ்ரீ வாதாபி கணபதியே
Okay, so I want to welcome our speaker of the day, Dr. K. Subramanian. He's a CEO and head of R&D at Power Gear Limited. He's also our alumnus from 1995, BTech Mechanical Engineering. He's one of the fortunate few occupants of Research Park. He has an office there. I think tenants in Research Park have to earn credits by doing stuff with IIT Madras. So I think he's doing this because he wants to make some credits. But anyway, we are very thankful that he has accepted our invitation and come here to give us this talk. He got his PhD from Cornell University in electrical engineering, specializing in MEMS, microelectromechanical systems. His current work involves implementing several novel technologies in energy and other sectors. Previously, he had worked with GE's Global Research Center in New York. He has more than 50 patent applications in his field. He managed a large program on MEMS at GE and received 2 prestigious awards for his research. One of them, the Hull Award, is presented to early career researchers at GE Global Research who have contributed significant technical achievements or a positive influence on fellow technologists and embraced GE values. Maybe he can tell us what they are in his talk. Because the other award, the Whitney Technical Achievement Award, is for a project that is viewed as a potential market game changer. He is a Six Sigma black belt. He has made significant contributions to many unique projects. He has authored numerous publications and technical reports. And he is currently carrying out some R&D initiatives at Power Gear that aim to showcase India's innovative talents to the world. So it's very fitting that the topic of his talk is philosophy, technology, and movies, the innovation recipe. I invite Dr. Subramanian to deliver this talk.
Thank you, Professor Nagarajan, for a wonderful introduction. I see we're about half full, so would you guys like to come a little forward so that we can have better interaction? Because I'd really love this talk to be very, very interactive. Great, thanks. Okay, thank you. As I said, I'd love this talk to be interactive, so please ask a lot of questions. Please give me your comments. Please tell me if you agree or disagree with the ideas that are going to be presented here. And please stop me mid-sentence, right, if you have a question. Just raise your hands. Okay? Okay? Thank you. Okay, so I'm here to try and talk about what the innovation recipe is, right? Is it possible to define a process or not to help you come up with new ideas, right? That's the big question. I mean, as you know, industry survives on innovation today, right? I mean, people have realized that it is not possible to survive in the long term without innovating, without coming up with new products. And the biggest reason behind that is whatever existing products a company makes, there's always competition and there's always price reduction in that product year over year, right? So the same product you make next year, you have to sell it at a lower price. So very soon you will end up at a point where you don't have any profit, right? So that implies that you'll have to keep doing something new so that you can make some profit in your business and you can sustain your business. So that's become very apparent in today's market. The fact that innovation is essential and we cannot survive without innovation. Just to tell you that innovation is not confined to technology. It's confined, it is available in all areas. I mean, when we invented missed calls, right? That was an innovation, right? It is possible because incoming calls are free in India and you can make missed calls. In other countries, people actually charge you for incoming calls, and even if the call is missed, it's incoming, so they charge you for it. So it was a direct outcome of the fact that incoming calls are free in India. So that was a classic example of innovation. Okay, so back to the main topic. How do you innovate, right? Is there a way you can come up with new ideas? Because that's the need of the hour. And we'll touch upon all those topics, right? And the topic of movies was here more as a crowd puller, right? That's why all of you came here, right? So movies and cricket and food, those are three things that attract people, right? So how many people have heard of the word Vedanta? Okay. How many people know what it means? So I see one hand, two hands. Okay, so Vedanta is actually two words. The first word is Veda, which is knowledge. Okay, the second word is Ant. Ant means end in Hindi or Sanskrit, right? So Vedanta is a word which means the end of knowledge. So does knowledge have an end? What do you think? I see a lot of nodding heads. No, right? So I think we all believe that there is no end to knowledge. You can keep on learning, right? I mean, there's a lot of knowledge out there, and we are only scratching the surface. So why would there be a word called Vedanta in our own system of philosophy? Any thoughts on this? So there is a field of study called Vedanta, which self-proclaims that it is the end of all knowledge, right? Okay, to explain that, I'll give you another example. What is the end of all numbers? There is no end. What is the end of all numbers? What's it called? Infinity. It is called infinity, right? So we invented this word called infinity to describe a concept that really doesn't exist, right? We said the numbers don't have an end, and now that's a little unsettling to the human mind. So we decided we will invent a concept and give it a name called infinity, so that it is useful for us to talk in terms of infinity, right? Then all of a sudden we know what it is to, what is the last number, right? So it's infinity. Easy answer, right? That's what Vedanta is. So Vedanta is infinity. It was a concept that was invented. Obviously the inventors knew that there is no end to knowledge. They said, okay, now let's capture that in a word so that we can define it, right? So that we can use it in everyday parlance, right? So that's what Vedanta was. Vedanta is infinity. Now, let's go one step further. Now, if knowledge is infinite, which is what the word Vedanta is telling you, shall we dissect it? Shall we divide it into two pieces? One piece is the sum total of knowledge that we know today. The other piece is the sum total of all knowledge that we don't yet know today. Fair enough? I'll just repeat myself. So we're dividing infinity into two parts. First part is everything that the world knows today, the sum total of all knowledge that exists, right? Part two is the sum total of all knowledge that we don't yet know today, that we will hopefully invent in the future. Or maybe there's some knowledge that we cannot invent ourselves, or maybe not. Maybe we will invent everything. Fair enough? Okay, so let's explore the first part first. Okay? First part, all the knowledge that's been invented today. Everything that's been invented, discovered, everything that is known in the world today. Okay? How do you innovate within those parameters? Right? Do you agree that there's a lot of invention to happen even within the knowledge that's available today? Right? You have textbooks. That's what you're here to learn, right? You have various courses, you have textbooks, you're trying to learn what other people have written. But then you're trying to use that as a basis to combine various facts and come up with something new in the future. Right? That's what engineering design is all about. You're always trying to design something new. So, how many people have heard about this Russian acronym called TRIZ? Okay, few people are here, right? So not too bad. I think I saw at least half a dozen hands go up. That is an acronym that stands for Theory of Inventive Problem Solving. Okay? So Theory of Inventive Problem Solving. If you write that in Russian, you get TRIZ. Okay? So for the benefit of folks who didn't raise their hand, TRIZ is an attempt, or was an attempt, to capture all the knowledge that people had today. Okay? So somebody just decided, okay, now I'm going to try and summarize everything that's been invented. Okay, they said, I'm going to study all the patents out there, all the literature out there, and I'm going to try and summarize. I'm going to try and boil it down to what physical principles they were working on, and I'm going to try and summarize what people invented. I'll give you a few examples. Before I give you the first one, TRIZ assumes that when you design something, when you're trying to innovate something, you end up typically with an engineering contradiction. Okay, in other words, you get stuck somewhere. Right? So you're trying to design some mechanical system or electrical system or whatever it is. Typically, you get stuck at some point. And that point is typically an engineering contradiction. A very simple example is, you're trying to increase the strength, you end up with something heavy. Right? Classic mechanical engineering contradiction. Strength and weight typically don't go hand in hand, right? If you're trying to make something stronger, it is typically heavy. Right? So TRIZ simply has a matrix. It's got a huge matrix of all the engineering contradictions. Right? One contradicting parameter is on one axis, the other parameter is on the other axis. So it has got this matrix of contradictions that you can simply go and look up. So if you land up in this problem where you have, you want strength, but if you increase strength, you're also increasing weight, but you want to decrease weight, you go and look at the strength and weight contradiction, and then it actually refers you basically as simple as a bunch of page numbers, where it tells you, okay, this is what people have done in the past for a similar contradiction, right? And it gives you lots of ideas. It says, okay, now make it hollow, so you'll get the strength and the weight. It says drill holes, right? So it gives you basic ideas like that. It says, okay, this is what other people have done in the past to similar problems. I'll give you more examples. There's a classic problem of, I think most people have used a rubber hose, right? You use a rubber hose to put water in your garden, right? And what is the basic property of a rubber hose? Why is it made of rubber? Because it has to be flexible, right? It has to bend around corners, and it has to basically transport the water to any corner of the garden, right? Now there are versions of these rubber hoses where you have to attach other parts to these hoses, like sprinklers, and you may have to take a tap in the middle of the hose and connect a branch to another hose, right? So there is a problem where in certain cases you have to machine this rubber hose. Okay, so machine as in classic machining. You have to drill a hole in it or something like that, right? To be able to access the water that's coming into it. So again, here is another engineering contradiction. You know from all your years of workshop and filing and so on that if you have to machine something, it typically has to be a hard object. Right? It's very difficult to precisely mark and drill a hole on something as soft as rubber. Correct? So you end up with a contradiction here where rubber has to be soft because it has to be flexible. The same rubber has to be hard because it has to be machinable. Right? So how do you solve this? Any ideas? Come on, we have a whole bunch of IIT students here, right? Okay, so I'll give you the idea. I'll ask you the next question again. So what TRIZ does is, if you say hard and soft, if you look at that contradiction, it asks you, it basically asks you a very basic question. It asks you whether you can separate these two constraints in time. In other words, does the rubber need to be hard and soft at the same time? The answer is no, right? Because it needs to be hard when you're machining it, and it needs to be soft when you're using it. And then when you answer no to that question, it gives you a bunch of ideas. It says freeze it, right? Freeze it. So when you're machining it, and this is actually done with rubber, in case you were not aware. So people actually freeze rubber, machine it, and then they later thaw it so that it becomes flexible. Simple, right? So TRIZ is a wonderful tool. I mean, in case you haven't seen it, I mean, I'm not here to market TRIZ, but I'm just saying this is a nice idea to compile solutions that people had invented in the past. Right? So why are you reinventing the wheel? You can always go back and refer to something else that someone else has done in the past and use it for your own problem. Right? More examples. Very simple ones. Has anyone wondered why lorries in India are small while lorries in the West are big? You still need to transport goods, right? Roads are small, right? So turning radius is the big deal, right? And it's a huge deal for lorries because you see lorries turning into extremely small streets and you wonder how they do it sometimes, right? So that's another engineering contradiction, right? The lorry has to be big because it has to carry a lot of goods, right? Because the storage portion of a lorry is actually only a small percentage of the lorry. I mean, you get a lot of overhead in terms of wheels and engine and driver space and all that. So ideally, you want to maximize the amount of storage space for a given size of lorry, right? So another contradiction, lorry has to be big to carry goods, but it has to be small because the turning radius is a big deal, right? How do you solve it? Sorry? Increase the road width, yeah, but that's a huge project, right? Yeah, how do you solve it in the lorry, right? Because you're a lorry manufacturer, how do you make a lorry that can do both? Yeah, so wonderful. I mean, obviously it exists in the market today. So the classic TRIZ solution to saying something has to be big and small at the same time is break it into smaller pieces. So you have a trailer. So you have multiple small sections with a link in between, so that it can negotiate the tight curves and it can carry a lot of goods, right? Very, very simple solutions. And again, you don't have to reinvent the wheel if you simply refer what other people have done in the past. Another classic example is a split AC. When air conditioners came, people were happy that it cooled, but it also made a lot of noise, right? So that was another thing called separate in space, where TRIZ tells you. It tells you that, okay, if you don't like one quality, you try to put that quality in a different space. So the noise making portion of the air conditioner is actually placed outside, and the cooling portion is placed, or actually the part that delivers the cool air is placed inside. So wonderful, right? You get the best of both worlds. Okay. Lots of examples like that. I was chatting with some of the folks in the alumni office, and we were mentioning that people derived ideas from Star Trek in the past. Right? You guys have seen Star Trek? It's one of the old TV serials. It's about space travel and all that. So there they have a device that gives you painless medical injections. Okay, so you get an injection and it's painless. Right? Any ideas on how we can invent something like that? So that is a classic contradiction again. An injection has to pierce you because it has to deliver the medicine. And to pierce, as you guys are all engineers, right? You need high pressure, small area, all that, right? To pierce the skin. So you need a sharp point and you have to pierce. At the same time, piercing is painful, right? So how do you pierce and yet keep it painless?